Just to recap before we get started, the volume of a solid of revolution using the disk method, if you're rotating around a horizontal axis, you're going to use this integral pi r squared dx. If you're rotating around anything with a vertical axis, your formula is going to be pi r squared dy. For these examples, we're going to set up but not evaluate an integral for finding the volume of the solid generated when the area bounded by the given curves is rotated around the specified axis. For this example, we have y equals x cubed, x equals 2, y equals 0, and we're rotating around the line x equals 2. So I drew the curve bounded by x equals 2, y equals 0, and shaded it so you can see the region, and we're rotating this region around the line x equals 2. So because we're rotating around a vertical line, it's going to be a dy problem. I'm not going to draw the actual region rotated, but I do need to draw r. Whenever you draw your r, you're going to draw it perpendicular to the axis of rotation. You start on the axis and you go towards the shaded region. So here's my r. Again, I arbitrarily drew it right there. I could have gone higher or lower. You'll notice r is a horizontal segment, so that's going to be important for later. And you can also see r is bounded by the curve y equals x cubed and the line right here where x is 2. So first I just wrote down y equals x cubed, and because this is a dy problem, we want everything in terms of y. So now I have x in terms of y. So for r, we're going to think about it right minus left. So on the right is x equals 2, and on the left is x equals y to the 1/3. So we can represent r as the expression 2 minus y to the 1/3. So again, just think of it as right minus left. Next, because this is a dy problem, you want to look at the shaded region and look in the y direction where the shaded region exists. So it exists from 0 all the way up to 8. This is the disk method, so we're going to do pi r squared for our formula. And again, we already noted that this is a dy problem. R is this expression right here, so we're going to plug that in. And here's our setup when we rotate this shaded region around the line x equals 2. For this problem, we have y equals the square root of x minus 1 plus 3, y equals 3, x equals 5, about the line y equals 3. So I have the square root graph that shifted right 1 up 3. Then we have the line y equals 3, x equals 5. Since we're rotating around a horizontal line, it's a dx problem. So to start, we want to identify r. So here's r. And again, you can see that r is bounded by the square root graph and the line y equals 3. Since this is a dx problem, we already have y in terms of x, so we're good on that. Again, r is top minus bottom. The top is the square root equation minus 3. So I wrote that over here. I have the square root equation minus 3. It's a dx problem, so look at the shaded region. So in the x direction, the shaded region exists from 1 all the way to 5. All right, and to set up, I pulled the pi to the front. You have the integral from 1 to 5. Here's your r expression, which is the square root equation minus 3 quantity squared dx. For this example, we have y equals x to the 4th, y equals 1, about the line y equals 1. Be careful on this problem because x to the 4th, it resembles a parabola. It's just a little more rounded at the bottom. Mine's obviously not drawn to scale, but you're bounded by y equals 1, and then you're rotating around this line y equals 1. So to start this off, we're going to draw r. Every single time r starts on the axis of rotation, you draw it perpendicular to that axis, and you draw it towards the shaded region. So I chose to draw r here. I could have drawn it over here. So you can see r is bounded by the curve y equals x to the 4th and the line y equals 1. Because we're rotating around the line y equals 1, it's going to be a dx problem. And so we already have y in terms of x here. To identify r, you're going to do top minus bottom. So it's going to be 1 minus the curve. So here's our expression for r. Because it's a dx problem, you want to look at the shaded region in the x direction. It goes from -1 all the way to +1, so those are going to be our limits. So I set it up, the integral from -1 to 1, pi, and then here's your r squared dx. I pulled the pi to the front. You might notice that if you were to integrate this region from -1 to 0, that would give you the same volume as integrating from 0 to 1. So some people will choose, because of the symmetry, to rewrite this as 2 pi, the integral from 0 to 1 of this integrand. So I just wrote that out. You could leave it like this, or you can write 2 and then times the pi integral only from 0 to 1 of the 1 minus x to the 4th squared dx. For this problem, we have y equals the quantity x minus 1 cubed, x equals 1, y equals 8, about the line x equals 1. So I took this cubic graph and shifted 1 to the right. So right here is 0, 0. You shift 1 to the right, and then you have your curve. Then you have the line x equals 1, and then up here is y equals 8. You're rotating around this x equals 1 line. Next, we're going to draw r. So remember, r is perpendicular to the axis of rotation. You start on the axis and you go towards the shaded region. Okay, so our r is bounded by the curve x minus 1 cubed and the line x equals 1. Because we're rotating around this vertical line, it's going to be a dy problem, so that means we need x in terms of y. So I raised both sides to the 1/3 power, and finally we're going to add 1. So here's x in terms of y. Finally for r, it's going to be right minus left, so on the right is the curve, and on the left is 1. So remember, you're going right minus left. Since it's a dy problem, look at the shaded region. In the y direction, it's going from 0 all the way up to 8. So here's our setup. It's the integral from 0 to 8, pi, and then we have this y to the 1/3 plus 1 minus 1 quantity squared dy. Remember, you can always pull the pi to the front. Just don't forget you need that constant value right there. You could also simplify these and cancel them out, or you can just leave it for the setup only.